And then we can ask, when we are going to see these speedups, right? So when we have device where we can run these algorithms. And you can see maybe to solve Shor's algorithm and like factor 200-digit number, you need millions of qubits, right? We need error correction. Might take, I don't know, 25 years if you're optimist, or I don't know. Polynomial speedups might take longer, right? Because we have to build a quantum computer. It has to be cheap enough that the polynomial speedup is worthwhile. And then this heuristics is more interesting, right? This is what I want to focus here in the next slide, because it might be actually much sooner, and it might be never, because you don't know yet, right? So we just have to wait and try. And what I mean by, and of course the challenge that I want to address here is just to try to find more algorithms, right? In each one of these 3 classes. You just get what you can get. So why this might be much earlier, these heuristics? Well, because we are entering this interesting era in quantum computing. So John Prescott termed it's noise intermediate scale quantum, NISQ. And the idea is that we're still a long time away from having a quantum computer, right, which can factor a big number. But these early quantum computers with maybe like 50 to 100 or a few hundred qubits and no error correction, that's too costly, we will have them soon, right? We already have some and we have more, and with better coherence. And with coherence good enough that we might hope to do something interesting, right? Unlike maybe some previous approaches where the coherence was just too short and there was some strong evidence that we could not do something interesting computationally there. And the big question here is whether these NISQ processors can do anything interesting, right? Then there is all this interesting work on just achieving quantum supremacy, just coming up with some problem for which you might show a separation. I won't talk about that. But I'm going to go more in the direction of the next step after that. Is there any problem which at least resembles something that you might be interested in solving in practice, which you could run on these machines, right? So that's one of the goals here. So what I think might be a candidate is this class of optimization problems. It's called semidefinite programming. What is the problem? So you optimize here over matrices. Okay, X is the optimization variable. The inputs of the problem, it's n by n S sparse matrix C, A1, AM, and real numbers, B1, BM. And also a number R, I'm going to explain what it is later. And the output should be a n by n matrix. And what you want to do, you want to maximize trace Cx. So it's a linear function on X. X is the optimization variable. And you have some linear constraints, which is trace AJX, smaller than BJ. And you have, that's the reason for the name, this positive semidefinite constraint, which says that X has to be bigger or equal than 0, meaning has to be Hermitian and all eigenvalues bigger or equal than 0. What is a particular case, which maybe is more well known? Linear programming, right? Just take all the matrices diagonal, the CA1, AM. This is a very simple linear program, right? With n equals 3, m equals 2. You can solve, right, in your head, right? That's easy enough. So what is the solution here? It's just, this, we should set this to 0, right? And then x3 has to be smaller than 1, and here x3 has to be smaller than half, so the solution is half, right? x3 equals half, and that's the maximum. So that's easy enough, but if you can, have many equations and then it gets more complicated, what is a very simple SCP? It's something like this, right? So you just, SCP where the dimension is 2, and the number of constraints is 6, right? You can put equality constraints by doubling the number of inequalities, right? And that's a very simple SCP, right? Just these are the Pauli matrices. So you want to maximize the expectation value with sigma z, where the expectation value of sigma x, sigma y is 0, and there's a quantum state, right? X is positive semidefinite, and the trace is 1, so it's like a 1 qubit density matrix. If you do some little math, you see that that's the optimal solution. It's like identity over 2 plus sigma z over 2. So that's simple enough, again, that we can do on your head, right? But what happens if you start increasing n and m, right? So then you cannot do yourself, but you can try to do on a computer. People care about that. They want to use for some applications. One that we see a little bit later is this interesting connection with approximating NP-hard problems. For example, max-cut and others. Turns out that NP-hard, you cannot solve them exactly, but you can look at the best approximation possible, and that's usually given by STP. And there's good algorithms too. So there are a few classes of algorithms. So interior point methods, they're very popular. They're usually used in practice, and they run like in this runtime, so m squared ns plus mn squared, and log r over epsilon. So when I mean solving, I will allow some error now. So I want to compute the optimal plus minus epsilon, and I want to satisfy the constraints also plus epsilon. Okay, I allow some small deviation of the constraints. But I still want it to be positive semi-definite. I don't want to put an approximation here. And this R, now I can tell you what R is. R is just an upper bound on the optimal solution. So take some X, which satisfies the constraint and is optimal. Take the trace of it, right? It's positive semi-definite, so the trace is a measure of the size. And R is just any upper bound on this trace, okay? Then there is another class of methods called multiplicative weights. It goes faster in terms of M and N, right? It's M times N times S, but much worse in terms of error. So it's like you choose, right? What you want to do. Okay, great. So this is like actually, you can prove this, right? These are rigorous runtimes. How about in practice, right? When people try to solve these SDPs, what is the largest size that they can run and what they usually do? I started getting interested in that recently, so let me tell you what I want, what I know. Maybe you can tell me more about it. So I found like 3 classes of methods. One is like interior points, the best available. This mosaic appears to be the best choice. There's this SDP, SPDA, and so on. Then there's this multiplicative weight methods. Actually, people don't quite use that in practice because the error is usually big, right? Because this depends on error. But I still want to compare what we could do if you wanted, because I want to compare later with quantum. And there is a heuristic method. It's quite interesting. It's called the Burr-Monteiro method. It's kind of nice because SCPs, they are convex. That's why, right, people like them. Actually, they turn into a non-convex problem, but with smaller matrices, like n by square root of n matrices. And then they actually prove that under some very general conditions, local minimum is an optimal minimum as well. So you can solve this pretty quickly. So what people manage to do is to have m very big, the number of constraints is very big, but they get stuck at n quite small. Okay, so here are some examples. So suppose you want to do this STP from XCut. It's called Goemans-Williamson. That's the form of it, but it doesn't matter, just in case you want to check. What I want to show is this plot, right? So n, the dimension will be the number of nodes in the graph. M is roughly n. And the sparsity is number of edges over number of nodes. So you can see that, right, when capital N, the dimension is 2,000. This already takes, and these 3 methods are this heuristic, and these last 2 are interior point methods. So interior points performs worse, and you can see that it already takes like a few hours, right, for 20,000. Now to compare later, what is 20,000? What is the log 2 of 20,000? It's like 14. So if you would store this as in a quantum memory, right? 14 qubits is already kind of like you get into a few hours, right? And yes.
So these are average case runtimes then, or is it like the worst case?
This is for the graphs that they tried. They have these families of graphs, right? These examples, particular examples of graphs with this number of nodes and edges, and then they just try and they compare, and this is what they got. Yes.
So while you say 14 qubits would be needed in order to encode that,
yeah.
What about the complexity of writing the circuit that would end up describing the actual equations and the constraints?
Oh yeah, I'll get to that. I'm just saying, forgetting about that, right? So 14, this is just like a rough thing that we get more precise later. But right, I'm just comparing that. If you would count as like in logarithmic scale, this gets stuck pretty early, right? That's all I'm saying at the moment. Any other question? Okay, then just another one is when you go to like parallel solvers, right? Parallel interior point solvers. Then there is some papers you can check. This is the number of cores, 1, 2, 4, 8, 16. This again is another benchmark. These are benchmark examples of SCPs that people like to try. These particular solvers that they use. So I got here one example, for example, right? Not to lose time. So with n 11,000, m 1,800, sparsity 10, it already 16 cores. It already takes like 8,000 seconds. So again, right? And that's that on log scale. That's 13. Okay, so again, another number to have in mind, right? So, so this is actually when you run this right in practice. But now you can say, well, actually, let's just look at some clear limitations, right? If you just want to store the matrix X, this optimal matrix X, this takes time n squared, right? And if you use this heuristic n to the 3/2, right, using this more Monteiro hack, right? Even though AI might be sparse, the input matrices, and usually we take them sparse, the point is that X doesn't have to be, right? X will be some full rank, like there's no sparsity there. So if you just want to store this, like 2 to the 35 is clear limits, right? Even before, right? But that's clearly something you cannot store X there. Then there is this other method, multiplicative weight method, what is interesting is that it can solve the SCP without actually having to write X explicitly, right? So we'll see how to do that later. But it still has this runtime, which is like linear in 8 n m log n 1 over epsilon to the 5. So how they do that, we'll see, but it computes matrix exponentials of linear combinations of input matrices. So you can basically work in the logarithmic of X instead of X, and this might be sparse again. This is sparse again. But right here, there is some clear limits, right? So if you just take, because epsilon like 0.1, which is big, but something, right? It shouldn't be bigger than that. Then 2 to the 38 will clearly be a limit. In practice, people get much, much lower than that, but that's a limit, So I'm giving these numbers because, once you look at the near term, we're going to compare with them, right? So this is another limitation. And even if you don't want to write X, we just want to compute the optimal value. We don't know how to do better than that, right? So we don't have any other approach at the moment. So the question is whether quantum mechanics can help now, right? So this is what I want to discuss. And I will show you that, yes, it can. And I'll tell you two kinds of results. One is if you have a universal quantum computer, and I'll tell you the runtimes you can get, and so on. And later I'll get you what we might be able to try in the near future and see if you can get something. So there'll be these two parts. But both, the idea to find these results is to connect this problem to another one, which is to compute thermal properties on a quantum computer. So why there is this connection? Well, it's simple to see. It just follows from this result. Due to James in 57. So James was working on foundations of statistical mechanics, and he found this, right? It's called principle of max entropy. So what it says is that if you have a density matrix rho, and you have some observables, AI, and this has some expectation values on rho, let's call CI. Then there is a Gibbs state, and when I mean a Gibbs state, it's just a state which can be written as the exponential of some Hermitian matrix. Any state can be written like that, right? Any mixed state, but this is particular because actually the Hamiltonian is a linear combination of the AIs, the observables, right? So this lambda I, you can think of some kind of Lagrange multipliers. They are just some real numbers you have to find. But this has, right, this is restricted, right? It's just a linear combination of the observables, which have the same expectation value, okay? So all you care about the expectation value, you could just, in place of rho, consider these states.
Sorry, Fernando.
Yes.
Is there any condition on the AIs?
Hermitian.
Yeah, but they don't have to be independent of common to each other.
No, they can be anything. Yeah, they can be just one of them. Yeah, it works. Yeah. So why this is good for SCPs? Well, look at the SCP that we have, right? So we have this. So I'm claiming that by the James principle, there is always an optimal solution of this form. Okay, optimal solution, which is the matrix exponential of a linear combination of the input matrices, and then you have to work hard to find lambda j's, but it's already restricted, right? Why that's the case? Well, because first, by construction, this X is always positive semi-definite, right? It's the exponential of a Hermitian matrix, so that's positive semi-definite. Second, let's take the optimal solution, X optimal, just normalize it, okay? Let's apply James' principle. So then we get another state which has the same expectation values as this guy, of this form, right? But if it has the same expectation value, it means that it must have the same optimal solution, and it must satisfy the constraints as well, right? Because they all care about the expectation values with C and AJs. So this guy must be an optimal solution as well, right? So there might be others, but we don't care, so we just can take this one. So now what we have to do is to find these lambda j's, right? So our way to solve SCPs is just to use these ansatz for the solution and just look for the lambda j's, right? And that's what actually this multiplicative weight method does, okay, as we're going to see later. But that also gives us a strategy for using quantum mechanics here now, right? So we can just, use procedures to prepare thermal states on a quantum computer, right? We can estimate the traces using, just measuring the observables AJ and so on, right? So if you use all these tricks, and I'll tell you later how it is done, we get these results. So there is a quantum algorithm for solving SDPs, running time T Gibbs. I'll tell you what this is. This is the main thing, plus square root of m. So we get some polynomial speed up in the number of constraints, and some polynomial in S in 1 over epsilon. Oh, here should be R over epsilon. I'm just assuming R is 1 here. I forgot to change this from another version. So the input, okay, but now let's be more careful. What is the input? The same from before, okay, classically. I put this normalization as well. I should have mentioned before, but I always assume that the AIs are smaller, the operator normal is smaller than 1, just a scale to the problem. But what is the output? Oh, actually the output here is different now. So I don't want to write X in a piece of paper. I want to just prepare on the quantum computer a density matrix given by this. X over trace X, where X is an optimal solution. I want to compute the value of trace X, and I want to output an approximation of the optimal value as well, okay? So you see that the output is similar to what happens in HHL for linear equations, right? So we output in quantum form. And if you want, you could do tomography here. But if you do that, it takes n squared again, right? But you can also compute some other expectation values, so it might be useful you can compute all the properties of the solution without having to do full tomography. And you can, of course, compute the optimal value, right? Which maybe is what you want.
Fernando,
yes.
Before you go back to 2 slides.
Yes.
So what's the freedom here between all the different x's that satisfy the above constraints? I mean, is there a gauge group, or is there some other organizing principle for understanding the degeneracy solution?
It's a good question, but I don't know. Yeah, I don't know. So if what we do know is that this. So if the solution is full rank X, then it must be of this form. This you can show. But might be many lambda j's that satisfy this. This I don't know, for example. If it's not full rank, then you can only approximate as well as you can by this, but it might not have this form exactly. So I don't know, actually. That's the honest answer.
Is the size
Yes.
of the family that satisfy this constraint depends on J or on M, on the number of constraints?
I don't know that either. I don't know. Yeah, I'm happy just to get any of the possible optimal solutions. What is the input model? This will be important. Or maybe this is like input model 1. So we assume just a normal model for Hamiltonian evolution, for example. There are oracles for which with unit costs we can compute the matrix element in all the non-zero matrix element in each one of the input matrices. Okay? So there's like registers J, K, L, Z. They are the choice of the matrix, the row, the Lth non-zero element, and they just XOR with the 4th register this matrix element, right? The Jth matrix on the kth row, and this function just is a mapping between this list for the S non-zero elements to the position where they are, right? So kind of the oracle knows where the non-zero elements are, right? And that can help you. What is this T-Gibbs? Well, that's the main thing, which is kind of like we have to understand how big it is usually, right? But you can informally you can think as just the time it takes on the quantum computer using whatever method you're using to prepare these mixed states, right? So this is a mixed states you can prepare on a quantum computer. Maybe you don't like mixed states, you can prepare a purification of this guy. That's fine, right? But then you must prepare this guy, and then we take, these new eyes, we don't know what they are. There's a bound on how big they are. We'll get to that later. But this will be just some upper bound on the time it takes to prepare this, right, those guys. Okay, so what is, let me just tell you a little bit the history of this. So there was a paper of mine with Chris where we proved first this like T Gibbs times square root of MS and this terrible number, right? R over epsilon to 32. But luckily this was improved a little bit after that by Apeldoorn, Gillian, Gribling, De Wolf. So they got kind of the same T Gibbs square root of MS, but R over epsilon to the 8, much better. Then with Kalev, Lee, Lin, Svor, and Wu, we actually saw that we could do the sum instead of the sum of T Gibbs and square root of M, and the same dependence on the error. And then Apeldoorn and Gillian, they improve again the dependence on error. Okay, so it has been going down, the dependence on error. It's and now we know this kind of tight. We cannot do something better than that. Okay, so as you see, one thing we could do is just run this kind of a heuristic, right? So we just try to prepare this as fast as we can, and if the instance is nice enough, if the matrices are nice enough, and I'll tell you what I think might be some examples later, this formalization will be quick. And what I mean quick? Well, kind of polynomial in the volume, right? Which is the number of qubits, which is polylog the dimension of the matrix, which is the capital N, right? So if that's the case, then you might have something much faster than what you can do classically, right? But not always is the case, of course. You cannot prepare these Frommel states always efficiently. It might take a long time. But if you have a universal quantum computer, there is some things you can say, right? So oops, here, I'm sorry. It should be all capital N and capital M. I forgot to change. So if you use amplitude amplification, there is work by Vossian and Pullan. They show that this T Gibbs is always upper bounded by sparsity times square root of n. This n is the dimension. It's the same as capital N. Okay, I just forgot to change. So you have this kind of Grover speed up, right? So this shows that the worst case complexity is like, if you forget the error, is square root of n, square root dimension, plus square root number of constraints. And you can show this is optimal. So, it's kind of, that's the best you can do. But maybe you're not happy with that. So is there a way to get larger speedups, right? Then we found a way that still we have to think more about it. But it looks maybe intriguing, which is changing the input model. Okay, so there's another model of inputs that you can propose, that you can consider. And if you do that, you in some cases, you get a larger speedup. So this is input model 2. Think about HHL again. This is getting more in the direction of the formulation of HHL. So now we say that these AIs, the input matrices, they are given in quantum form. Okay, so they are given as quantum states to us. For simplicity, let's assume they are positive semi-definite themselves. If they are not, there is a trick you can do. But if they are, then we assume that they have a procedure to efficiently prepare those mixed states, AI over trace AI. Okay, and there will be a parameter which is based on how big these AIs are, right? So it's the maximum of AI of trace AI. And the bigger it is, the worse it will perform. Yes?
Just to get something clear from me. When you think of a Gibbs sampling,
yes.
There's a problem. Let's specifically take a Gibbs sample, then there's this notion of temperature, right?
Correct.
So I could prepare a higher temperature state much more efficiently in principle.
That's right.
How does this influence the performance of the SDP solver?
Yeah, I'll get to that, but the answer will be that the temperature they have to go. If you normalize like in the physics way, that's why it will be linear in the error, in the accuracy in epsilon. Yeah. And then what Appledon and Gillian showed, improving on the result that I had with Kalev, Lee, Lins, Vor, and Wu, is that in this setting, actually you can get something better. The T Gibbs is polylog in n. Okay, so again, I'm sorry, this should be like small n is equal to capital N in this slide. And b square. So now always is well, first you cannot claim it's exponential speed up because it's a different input model. Second, many instances this b is pretty big, right? So that then won't have a speed up. But if all the conditions are satisfied, then you might be much faster than before. So in that case, the total runtime will be something like this, right? Square root of m, polylog in n, b square, s square. This small r, we don't have to use it here because over delta is epsilon, sorry, to the 5. This is an old slide, should have changed. So I like to compare this with HHL, right? So HHL, linear equations, AX equals B. If the vector B, if the BIs are given as a black box, like in input model 1, right? Where you just query and then one position and it puts back the value. Then you need square root of n time to run, to solve linear equations, right? Because you can reduce to, search problem can be reduced to this setting, right? So what was the insight is that if you change the rules of the game, if B is given as a quantum state, then you can have polylog runtime, right? But there as well, there was another condition, another effect, which is the condition number, right? And only for a small condition number, things work fine. So roughly, this B is playing the role of this condition number here, right? But whereas condition number is very well studied and it's clear the interpretation and so on, this B, I don't really know what it is, right? So it's kind of, is open to try to understand this better and the connection with HHL. Right, because actually linear equation is a particular case of SDPs, right? It's a particular case of a linear program, which is a particular case of SCP, right? So it makes sense to try to make this connection with HHL better, but we don't know how to do that. Okay. Right, so now you can say, great, so maybe you only care about these, even these polynomial speedups, and right, that might be interesting. But there is a big elephant in the room, right? And that's this part of the runtime, R over epsilon. And why that's a problem? Well, that's a problem because for many applications, in particular if you want to solve combinatorial optimization problems, they have very large R over epsilon, okay? Usually scaling with n, with the dimension. So if you just try to apply it, you don't get any speed up, right? Which is said. Then what we're trying to do now is actually to change the algorithm for this case and try to get some speed ups. And we could do that so far for one problem, but I just want to mention briefly. And that's for the, maybe the most well-known SCP, which is to approximate max cut, right? So this is a result with Daniel Franz and Richard Kung, going to be out this week or next week. So we can show a speed up for Goemans-Williamson SCP for max cut. A very minor speed up, but nonetheless a speed up. So classically, you can solve that in time. N is the number of vertices. D is the degree of the graph, okay? So it's clear that classically you need at least time linear in n times d, right? Because if it's less than that, you cannot even distinguish two graphs where one has a much larger number of edges than the other one, right? But quantumly, we show that you can solve in this funny runtime, n squared over square root of d. So not for all this, but if d is large enough, right? So then you get a speed up, right? Smaller than quadratic, right? So but at least you're getting some. So let me tell you briefly about it. So what is the SCP? Well, if you have a degree z graph with n vertices, let the adjacent matrix of the graph be A. And then this Goemans-Williamson SCP is the following. You want to maximize trace AX, where on the xii, they are all equal to 1. And x is positive semidefinite, okay? So Goemans-Williamson famously showed that if you can solve this problem, you have something like of a 0.7, and I forgot the rest, approximation ratio to the optimal solution, right? So for general graphs, which was a very interesting result. But now what is the problem here? You can show that the trace of the optimal solution scales like n times d. And you can show that the operator norm of A is of order d, whereas the optimal cut is of order n times d. So if you just put in the previous bound, in the previous result, this would scale terribly, as a big polynomial in n, so no speed up. But now, if you just want to approximate the cuts, actually it's enough to solve this SCP with additive error n times d times epsilon, okay? And now you can renormalize to put in nice form using quantum states. So believe me, I won't show you the results, but actually it's enough to solve with additive error epsilon as before, the following SCP. Where now instead of adjacency matrix is adjacency matrix over degree. You want to maximize trace A prime rho. And rho is just a density matrix, but all the diagonal elements are equal to 1 over n, okay? So this is what you want to solve. Okay, so that's the problem, right? But now here you can see what is the challenge, right? The challenge is that quantumly we can always get the constraints up to some error epsilon, right? And but this is so small, right, that this epsilon has to be of order n, right? And then you're screwed, right? Because it goes as like 1 over epsilon to the 4, right? So what is the idea here? Well, the idea is that instead of all these constraints, right, we have n of such constraints, we can bunch them together into one constraint, okay, and then try to explore that. So we are going to relax actually Goemans-Williamson and just saying that actually we have this problem now. So we have a quantum state, rho. This is the dephasing, okay, it just outputs diagonal density matrix with the same diagonal elements, right? This cat I is the computational basis. And now we wanted this to be close to the maximally mixed states in one norm, in variational distance, okay? So this is like just allowing some small error in each one of them, but the total errors, right, of this approximation has to be bounded by epsilon, right, instead of individually. So we treat this constraint of like this phase state being close to maximally mixed, right? So if epsilon equals 0, that's exactly equal to that, but we allow some epsilon now. And we treat this as a single constraint, okay? And that's basically the main idea from the previous solver. So you just actually formulate in a different way the SCP and try to solve directly, put many constraints into one and work them as before in the method that I haven't shown you yet, but we'll get there. Okay, so there's some other applications. So in this paper, we show that this quantum input model, we can learn the class of low rank measurements on n qubits in time polynomial in n. So now n is the number of qubits, right? So that's, and in the Upperdoor and Gillian, they give some other applications. I don't want to get into that. So that's the first part, right? That's what we could do if you had a quantum computer, right? A universal quantum computer. Is there any questions here? Yes?
So when you have the ability to compare the Gibbs states using a single query,
Yeah.
the question is, do you have the ability to compare the true Gibbs states to single query, or is it a purified Gibbs state?
So there are methods that prepare the purified Gibbs states. There's some other method that actually prepare the density matrix, the mixed state.
Right.
And either is fine here.
Okay, so you don't explicitly need
Oh, so it depends on the. No, you don't.
Okay,
You don't.
cool.
Yeah,
That's cool.
that's right. Okay. So now I want to get more like in heuristics territory. But to do that, let me make a connection, which is very simple, but it's good to know, which is that actually what we're trying to solve here now is strictly an extension of this quantum annealing problem, right, that is very popular and people like to study. Why? So let's see that, well, first, if you want to compute the maximum eigenvalue of a matrix, that's a very simple semi-definite problem, right? So you have a matrix C, you maximize trace X, where X is a density matrix. These are the constraints. So the solution is just the maximum eigenvalue of X, right? X is Hermitian. Maximum eigenvalue of C, right? And C is Hermitian, because C is Hermitian. So what is this quantum annealing problem? Well, we have this C, which is usually, right, it's just some classical Hamiltonian. So it's diagonal in the computational basis. And encodes some, right, spin glass or, I don't know, max cut or free set. And you want to prepare, right, you want to compute the minimum energy just by cooling down, right? So here you could just like cool down minus C. So this is one example for max cut, for example, right? So C in that case, you have some, variables for the vertices of the graph. You want to find the maximal cuts. And then it's just this, quadratic expression in these variables, right? Where I is connected to J if they have an edge there. And the max cut of G is just the maximum eigenvalue of C, right? But now, why this makes sense? Well, note that C, the dimension of C, is exponentially big in the number of constraints, right, of the combinatorial optimization problem, right? So even though there is polynomial time algorithms for computing the maximum eigenvalue, this, right, just doesn't translate into the original one. So, basically what we're doing is, right, looking at a generalization of this class of problems, right? If you look in this way. But then we can compare, right, like this quantum annealing versus quantum SCP. And there is some interesting differences. So first, the Hamiltonian in quantum annealing usually want a classical, right? You want to solve some, free sats, for example, right? But for SCPs, it makes sense to consider the general quantum Hamiltonians, right? That's inbuilt in the problem, right? And usually, the interesting SCPs, they will be really quantum. If not, it's like an LP, right? It's a simpler problem. The temperature for annealing, we want a 0. Oh, this should be actually delta. Sorry, it was improved. So we're going to see that quantum is of order delta square, where delta is what I call epsilon before. Sorry, I should have went through these slides. So the temperature goes with the accuracy. If you allow some high accuracy, then the temperature can be higher. So that might be helpful. Preparation for quantum annealing, we know many, where we can cool, we can do a Zabasky evolution, we can do this QAOA. SCPs, we can of course try to cool. We can do some Gibbs sampling, but we can also do dynamic equilibration, which we'll see next slide. And both are, at least in this formulation, heuristics, right? In the sense that in quantum annealing, we have to understand the minimum gap throughout the Zabasky evolution, for example. This might be very small, right? And we don't have control. And this depends on the instance. For SCP, I think the analog of the minimum gap is this T Gibbs, right? That's the same, that's this order quantity, which is, right, it's even like a gap of some kind of, right? The transition matrix of the Markov chain, right, which defines the Gibbs sampling. It's very hard to compute usually. It might be very small in the worst case, right? And we have to try to handle it. But I think these SCP solvers, it might be easier to achieve an advantage with them, and I'll tell more details now, than quantum annealing, because in a sense they're exploring more, right, the fully quantum features of the device, right? So, if you're trying to go in this direction, we should try to go as quantum as possible, right? And they allow you to do that. Yes?
But if the runtimes are really the minimal gap, then it's not really a heuristic, then you prepare exactly the ground state, right?
That's correct,
So
yeah.
say if you do it at higher temperature faster, then it's a heuristic.
Yeah.
Okay.
Or if you yeah, that's right. Or if you don't know the minimum gap, right? And just, yeah, right, yes.
So when you say quantum annealing, it sounds like you're more talking about adiabatic state preparation. It seems
I'm bunching everything to quantum annealing, right? I'm saying quantum annealing is you want to compute the ground energy or the ground state of some combinatorial optimization problem using quantum mechanics, right?
Okay, so basically what you mean is like any kind of heuristic approach in order to be able to...
That's right.
Okay,
that's
fair.
right. Yeah, indeed. Yeah, right. Okay, so maybe this is the algorithm, but I want to tell you in the end of the talk. At the moment, I'm just ask you to believe me. So now let's see how we would solve it on these NISQ devices if you want to try to do it, right? So as I would tell you, but I'm going to tell you this later only. In the simpler version of the algorithm, actually that's the runtime. Okay, it's worse, like C gives times m over epsilon to the 4. But the quantum part is much simpler, so that's why it's nicer. The quantum part is just, we compute expectation values on the input matrix AIs of the Gibbs states that we have throughout the talk, right? Or throughout the algorithm, which is, they are all of this form, exponential in linear combinations of the AIs. So how we would run it? So we will have a number of iterations, which is from 1 up to 8 log n over epsilon square. And then on the classic computer, we compute some coefficients in ui, okay? And we form a Hamiltonian, sum of I in ui ai. And then on the quantum computer, we prepare the Gibbs states, major exponential of that. And we compute the expectation value with the AIs. This we call Ci sub t. Then we send these coefficients, the expectation values to the classic computer. Very quickly computes a new set of new I t plus 1, and we iterate it, okay? Another claim is that at most, with this number of iterations, this works. You find a solution. And we see that in the, probably we see that in the end of the talk. So there is this is a hybrid, right? Quantum classical thing. Yes.
What's the sampling complexity here for this compute stage?
For this one.
Yeah.
So we're going to. You mean how long does it take to do this part?
No.
Or
after you prepared it to get an expectation value.
oh, 1 over epsilon square, right? If you could measure AI, if you could measure the AIs, right? Which, right, so I have to tell you what the AIs, but the AIs at the moment, they are just emission matrices, right? They're observables.
So you're making some sort of effective locality assumption.
We will do that next slide, that's right. But at the moment is, there is the complexity of implementing the measurement, right? That we have to factor in, and how many times we have to repeat 1 over epsilon square, right? To get accuracy epsilon in the estimates, right? So that's why, it goes to 1 over epsilon to the 4. It's 1 over epsilon square from here, 1 over epsilon square from the time you have to repeat, right, the measurement. Okay, but now as Jake said, right, so.
Wait. So
Yeah.
I hear you, but I'm not entirely convinced.
Okay.
Because an error in the CI is going to cost the computer. May not.
Oh, that's right, you need to do analysis there.
It may amplify, right? So.
But it works, right, so that's what the analysis.
Just take away that it works.
Yeah, that's right, I haven't proved to you, yeah, but it does, yeah, right, yeah. Once actually, hopefully I have time to explain actually the algorithm and you see that it's actually easy to see how it propagates. Yeah. Oh, I'm sorry. Okay, but now, all right, so what are the missing pieces, right? So, which AIs, when you can do that on a quantum computer is already hard, right? Especially on a small quantum computer, right? So when you hope to, for each AIs, you might be able to do this part here. And actually, for each AIs, you might be able to do it and classically still hard, right? So that's kind of what you have to achieve here. Okay, so what is the proposal? So in the near term, I'll be very happy if you can just solve SDPs which are not of practical interest, but it still show a quantum speedup, okay? So I'm working with people at Google, and there is, this particular, they're using superconducting qubits. No, but you could run this in other NISQs too, but I'm going to focus on this one. So they're using superconducting qubits. Basically, they have, that's the shape. They will have 72 qubits. So, superconducting qubits, you can model just as a bosonic modes in each one of these crosses. But they couple nearest neighbors, so they can hop, like excitation can hop from one to the other. There is also an on-site repulsion if you have more than 2 excitations, right? It's like a nonlinear harmonic oscillator there. So if you put together, it's kind of a Bose-Harbert model, what you have there, okay? So this is the Bose-Harbert model. Let me just tell you, this is the Hamiltonian they have in their system, okay, to good accuracy at least. So they have kind of these NJs, this counts the number of excitations in one site, the number of bosonic excitations, and they can tune, the strength of this. It's like some kind of chemical potential. They have this on-site nonlinearity, right? If you have more than 2 bosons, there is a penalty hit. This comes from having this anharmonic oscillator there. And they can couple the coefficient UJ too. Then they had this hopping, right? So, the excitations can tunnel from one to the other, only nearest neighbor, and they can control GI. And this is like a local field that they can put, okay, which has this form. AJ is the annihilation operator of the bosonic excitations. AJ dagger is the creation operator. So this is what they have. Okay, maybe you don't like bosons. I will truncate, of course, to qubits, but just wanted to explain that's what they have. So what is the idea? What I propose, first, choose a SDP as follows. A0 is identity, B0 is 1. This means X is a density matrix. Okay, we get rid of the capital R. That's great. That's the first thing. Choose as the other instances just different instance of this Hamiltonian, but now with different values of delta I, UI, GI, and FI. Okay, because this you can tune the way you want in the experiment. We have to normalize because actually this, the norm of this guy grows with the number of qubits, right? That's what I call like this physics normalization before. In the formulation, we want operator norm 1, so we have to divide by the operator norm, okay? So we just create this SCP instance. It's very artificial, right? Great. It's very artificial, but you can try to solve it. So just you want the numbers, they can do like U, 200 megahertz there, and just G, delta, and F in the range of 30 megahertz. You can, and we should, right, just to make it simpler, truncate the bosonic mode in each site to a finite number of bosons of excitation. So we can truncate to k equals 2. It's kind of good, but actually it's better accuracy when it's 3 or 4, okay? And in the end, we want to compare, right? I'm going to do some back of envelope calculation to see if it's feasible or not. We need more work still. But what they can achieve, or they think they can achieve, is that this, the lifetime, so T2, right, which is roughly half of T1, that's like 20 microseconds. So this you should think as the decoherence time there, at least some rough approximation, okay? So for example, if the procedure takes much longer than 20 microseconds, it's not going to work. If it takes less, it still might not work, but at least it might. So, okay, so how about this model, right? If Q equals 2, then we have a qubit Hamiltonian. That's kind of a simple model. We just have sigma z, individual sigma z and x and y in each site, and then you can control the coefficient the way you want. And the interactions between the different sites is the xy model. So you have xx plus yy, right? Which is just this tunneling of excitations, okay? And you can couple this, right, these coefficients. Actually, you could have here, the coefficient could vary from site to site, but I don't want to do that. So actually, this model, if you have this local control here, it's very broad. Actually, it's like QMA hard, even on square lattice. Okay, so you're so in very general class, but I don't want to do that. I want to keep it translation invariant, and you see why. Okay, so how about now? What do we want to do? We have to compute on the quantum computer these expectation values, right? Trace AJ expectation value, matrix exponential of this linear combination. Now putting everything together, the right normalization, this will be the right thing. So we have some numbers, lambda I, which sum to 1, and the inverse temperature now, right? And now this is really, the inverse temperature would be 4 over epsilon u, okay? So epsilon, just think about it as 0.1, that's the accuracy. I don't want a very I don't want a very high accuracy because we'll pay a lot. So think about 0.1. So we want the temperature to be like roughly 40 times lower than this U coefficient here, okay? Which is possible. It's like it's not within reach, but it's still how we do that, right? How we compute this expectation value. So you could try just to couple to a bath, right, and control the temperature, right, and hope for the best. But that's not the best approach because usually you don't have, the temperature is the temperature of the fridge, right, which you cannot control. And moreover, it's not clear that the system actually will go to the thermal state with this bath. Maybe there is some other effects there going on. I would like to keep everything coherent. Okay, so that I think is much easier. So that's this idea that because our AIs, they are special, actually we don't have to prepare the global Gibbs states. We can just prepare a state which locally looks like the Gibbs states, and that's enough. So that's the idea of this dynamic equilibration. So you have the idea here is that if you have a Hamiltonian, of course, if you let time evolve with Schrödinger equation. But if the Hamiltonian is what we call ergodic, okay, it's not always ergodic, but many times is, then after some equilibration time that we can try to bound, AIs, because they are sum of local observables, they will be very close to the expectation value of a thermal state at the same energy as the initial state, right? So psi 0, just take psi 0 as a product state. It had some mean energy. Energy is preserved, right? So the energy before and after have to be the same. But that's the only thing that is preserving if it's ergodic. Okay, so locally it looks like a thermal state as the same energy as the initial state. And then no, this is what I propose to do, right? So you just prepare product states with the right energy associated to the Gibbs state that you need. You time evolve, and locally you can estimate, right? And then you can estimate the AIs on the thermal state because they are some of local terms. Yes.
Ergodic here mathematically means that the matrix is irreducible?
No, it's there is no good mathematical definition. It really means that this works. So physics is like, we think that there are two phases, ergodic phase, and usually that's why I want translation invariance. Usually translation invariant models are ergodic. Then you have a lot of disorder. This goes to localize or many bar localize, right? And then this might take a long time. So spin glasses, this would take a long time, for example. But this model, because now you can ask, of course, is the model ergodic, right? And people did numerics in 1 dimension, is what they can do. I want 2 dimensions, because 1 dimension is easy classically. And they saw it is ergodic, okay? So I don't have time to go into the details. They saw it's ergodic, and the equilibration time, if I put all the coefficients, is on order like of half microseconds, using the same, the same numbers from before. So this will be, right, so at least for this 1D, it equilibrates pretty quickly. So you'll be fine. But of course, it's not what we want, right? It's 2D what we want. And then we don't know what happens. Okay. But now you can ask, maybe actually this instance that we have, they're very easy, right? We can do classically as well, right? And then, okay. And this we can never have a proof, right? So this is really like a fight between 2 camps, right? There's people trying to come up with better classical methods. There is the quantum computer, and who wins will change it with time, right? But of course, we have to check what we know so far and see if we cannot solve classically well, right? So usually the biggest obstacle, at least for annealing, is QMC, quantum Monte Carlo, right? And this will work very well if the local field, there is no local field, because then there is no sign problem. But if f and theta, they are not equal to 0, there is a sign problem, okay? You cannot map to a stochastic Hamiltonian, and there is not clear how Monte Carlo performs. But it's still, this sign problem is due to local fields. So if you talk to experts in Monte Carlo, they say, well, maybe it still works well, so we're doing it. We don't know yet the results, okay? But then you can try tensor networks, but because you want a thermal state here, you cannot do more than 25 sites. Even then, it's like pushing, probably. You can try to do the simulation classically using, exact diagonalization, like using this Krylov space method. 42 sites is clear limit, probably much, much smaller than that. You can try to explore localities in some kind of Lie-Robson bound way. Forget about this, we don't have time, but this will also perform poorly with the parameters that we have. So at least the direct candidates, they will not perform so well here, which is a good sign. But of course, QMC might do well, and that's a big risk. So we would like to get a richer problem, which is when you have a Bose-Harbert model with nearest neighbor interaction and next nearest neighbor interaction. Okay, so if you could do that on a quantum computer, that's great, because actually, first, physicists do not understand what happens here. They do not know the phase diagram of this. They think there might be a spin liquids when T2 equals half T1, but they don't know all the methods. They give different results, right? So that's like really looks like hard, right, to compute thermal properties of this guy. Now you can ask if you can do that on a quantum computer. You have to change to skip that, but we are studying a way where, but then you have to put some time control, some analog digital simulation. We have to understand the errors. I'll jump that. Okay, so that's the algorithm. Maybe I'll tell you very quickly how it is. That's the last slides. So what is the algorithm? Well, we want to find a simplest version. We just want to find a density matrix for which trace AI rho is smaller than BI. Let's just consider this particular instance. We can reduce the other one, the general case to that. So we want to look for the lambda i's in Jane's principle, right? And how we do it is interactive arguments. So we start with a guess, which is we have no idea what it is. It's maximally mix the states. And we just iterate. So each time from 1 to 8 log n over epsilon squared, first we do Gibbs sampling, and we create square root of m copies of rho sub c, okay? Then actually we search using Grover, and we can because we have this number of copies, for I such that the constraint is violated, okay? Right, this just means that the constraint is violated, the ith constraint is violated. If you find one, great. If you don't, then we are done, right? Because they are all satisfied, we output rho sub c. If you find the violated constraint, we call it I sub c. We just do a penalty, okay, some kind of gradient descent, but it's like we do that to the exponent, right? So to the matrix, we add in the direction, we add the constraint I sub c in the right for the violating constraints. And you can show this will converge, okay, in this number of iterations. But then, right, so if you use phase estimation and amplitude amplification, as I mentioned, the Gibbs simply takes times square root of n. So you need to prepare the square root of m copies. So that gives this square root of m times n, right? So that's like one version. There is better things you can do, but that at least gives one flavor. Okay, so sorry, I have to go a little bit fast in the end. So solving these SDPs, I think, might be a good application for quantum computers in the long term. Maybe also a good candidates for achieving quantum speedups in the short term, right? That's what I tried to tell you. It's still okay. First, we have to do some more theoretical work, right? Numerics and so on, benchmarking. Then, of course, we have to wait for the experiments and see, right? There's no guarantees here. This is tightly connected to finding speedups for quantum simulation, but now for thermal properties, right? And then you can say, okay, so what's the point? Maybe forget about these STPs, right? Let's just try to find, speedups for thermal properties, right? That's good enough. But I think, well, first, for some communities, STPs are more interesting than thermal properties, right? There might be. But second, I think actually this is a very good way to benchmark if you're doing the correct thing for these thermal properties, right? Because it's very unclear what you mean to simulate thermal properties. It might be to find the phase diagram or something like that, right? Solving these SCPs put this in a very quantitative way, right? Really, you have to solve this problem to that accuracy and output the solution. So I think that's a good way to phrase it as well. There are many open problems. So, can we find relevant series with large speedups? We don't know. What is the complexity of solving Goemans-Williamson, right? We have this tiny speedup now, but we don't know. We don't even know, I cannot prove any lower bound. It can be that you have exponential speedups. I doubt it, right? But I cannot show it at the moment. So that would be nice to prove lower bounds on it as well. How about general SCPs for combinatorial optimization problems? We only can get a speedup for Goemans-Williamson, but all the other ones, they're pretty similar, so maybe there is a way to do it. Of course, improve the dependence on R and error. Quantum interior points, interior point methods, classical, they perform much better in terms of R, right, and epsilon. How about the quantum interior points? There was an interesting paper recently on that by Kernel and Prakash, and we're going to hear about it, I think, today. And second, might this be an application for these NISQ devices, right? So that's all. Thanks.
So one of the things that I always worry about with NISQ devices is things such as coupler errors when you're setting the parameters for your Hamiltonian, especially because they come in exponentially in this. So my question is,
I didn't understand. What do you mean they come exponentially?
Oh, in terms of the Gibbs state, right? The Gibbs state is e to the minus.
Oh, I see.
Right.
Right. So that's a good point.
And so my question is, have you done any analysis to determine what range of coupler errors would be reasonable?
I did. Yeah, I did. And the nice thing is that it's kind of it's easy to understand the propagation. It's similar to what Jake asked you, but suppose that you want to solve this SCP instance, but instead of these coefficients, you have a little deviation, right? Which they do. They never can set it precise, right? So it's like a little deviation here and here and here and here. Now what you can show is that if each one of them is specified to error within error nu, the final error of your SCP, epsilon, it will become epsilon plus nu. So it's like linear in the error that they can do. And they can do that within like 1%. They think they can do at least. So this will not, this will be fine. So that's, so even though it's exponential indeed, because you only use this as a intermediate step to get this SCP. So so look at the original SCP. So if you just have some error in the matrices, right, they can just propagate, right, so linear thing, right. So that's basically the idea. Yeah.
So I'm kind of curious in this hybrid solver that
Yeah.
you're proposing towards the end. There's obviously a topology that describes this category of Hamiltonian set by the operators A and by the choices of lambda, and you have a sort of constrained plane on this operator space. But what I'm trying to understand is why prior information from the previous run must be thrown out or disregarded when you take the next set of values for your news, right? I mean, I feel like you're being a little inefficient there, right?
Let me tell you, this is the details of what I said before, right? I think the information is stored, right? So think about it. So you're at step T, right? And at step T, you have this rho sub C, which is a Gibbs state. So the Hamiltonian is just log rho sub C, right? So when you go to the next step, you keep the Hamiltonian and you just add something extra there. right? This wasn't clear in the first slide, but that's how it works, right? So each time you update the Hamiltonian in each step by just adding some extra penalty there. So you keep the Hamiltonian you already have and you add something else, right? What you add else is just the input matrix which was violated.
I guess I'm talking about the classical step of the algorithm, and I don't think that's a classical step because you don't want to.
Oh, that's a classical step. It's just because it's so simple, right? So the classical step is really just you estimate all these expectation values, you find the violating one, and then that's it. So you go to send it to the quantum computer. Now this symbol I sub c, right?
Yeah, I mean I know that, but what I'm trying to say is that your estimator for the expectation values for the next run, right?
Yeah, which are these guys, these numbers. Yeah.
Yeah. Okay, so clearly we're talking about different things.
Yeah,
Go
but
back a slide.
with this slide, go back to this slide, or to maybe to this one that you want, right? So let me.
This hybrid solver, there it is.
Yeah, right.
So can you tell me now from the algorithm you just described versus this algorithm, it's the same algorithm?
It is.
Okay, good. So the compute new stage,
Yeah.
this thing that you have, which is maybe,
Yeah.
maybe new and another variable could be used instead, so you can compute new, not new.
Right. Right.
So in this compute new stage,
Yeah.
you use this Grover's complex.
Oh.
It makes sense because it's on a classical computer, so I don't understand.
Oh no, right. So indeed, so that's why I said it's a simpler version. There is no Grover in this version.
Yeah, so
Okay.
this is the hybrid version I'm trying to get at.
Yeah. So first, there is no Grover, but it's still the same procedure. So you on the quantum computer compute the expectation values of trace rho sub t AI,
that's
right?
that's okay.
Great. These guys. These are the CIs, right? Now the next, and now we want to update. We want to compute the new i's t plus 1, right? And I'm saying that they're all the same except for one of them, where we add minus epsilon.
So my point is when I go back to the last stage there,
Yeah.
and I do this compute again,
Yeah.
I may not need as many measurements.
Right, but it's a bit subtle because even though indeed the Hamiltonian, you only add one term to it, because you take the Gibbs state of this guy, this Hamiltonian, it might change all expectation values, right? It might only change a little bit of them, right? But it might change all of them, right? So because you change the Hamiltonian, but now you take the exponential, right?
So I agree with the devil's advocate case that you're taking. But
Yeah.
I'd say
It might not.
time you won't have to.
Yeah, then it'll be great. Yeah, and indeed, you might also not just put a penalty epsilon. You might take a bigger step, right? And all these things, it's like as a heuristic you can try, but I don't know how they perform yet. But you're right, it might be better. But yeah, I don't know how to explore that, but maybe yeah, that'll be great. Yeah. Mario.
It's more like a remark that so when you compare the solver for NISQ,
Yeah.
quantum and classical,
Yeah.
so the 0.89 of Goemans-Williamson is like is a special. It holds for a special density. So for instance, if the graph is very dense,
Yeah.
then it's not necessarily the Goemans-Williamson.
Correct.
definite
Yeah.
is the best.
That's right.
So you would like to just sampling, for instance, or maybe some simpler thing. As a matter of fact, I think that when like the instance is completely like you have order of n square edges,
Yeah.
then I think it's not 0.89. It's like 1 minus epsilon.
That's right. Yeah.
Approximability.
That's right.
So there are other things.
Yeah.
When you make the comparison, I mean, it's fair. So if you
Yeah, so that's a good point, right? Especially like if it's really number of edges is of order n, then you have even a pitas, right? But what I want to run here is when the degree is of order, like for example, square root of n, okay? So when the number of edges n to the 3/2, because then there is a speed up, and there, at least I couldn't find, and I asked some people, I couldn't find anything better than Goemans-Williamson. So for this density, like when the degree is square root of n, yeah, it seems, I couldn't find any classical solver which is better than Goemans-Williamson. But there might be, indeed, there might be, but yeah.
Maybe just to latch on to what Jake said. For this thing, I mean, isn't this like if your observables are close to being commutative, right?
Yeah.
And they're close to independent, and if the corresponding news of the non-commutative ones are small, then they're not influencing the estimation, then you can ignore it and just sample the small twice. I mean, what I want to say is I think you can make it quantitative.
You might be able to, yeah. I didn't. I have to think about it.
Trivial,
Yeah.
but I think it would
Yeah.
It's a, you could use labor of extension.
something like that.
Yeah. That'll be nice actually if you can do it fast. Okay.
I have a question about the quantum Monte Carlo.
Yes.
You said that that could be classical way of simulating this.
Yes.
But with QMC, I mean, you can compute like diagonal expectation values, right, of diagonal operators, but these
Uh-huh.
are non-diagonal. So
I think you can also compute non-diagonal, no? Like
you're sampling classical distributions, which are like classical, like these strings. So
that's right, but you so you know if you have an off-diagonal one, right? Then you have this path integral, right? And now you have some ij here in the observable, right? So you
yeah, you can probably do some sort of linear combinations.
yeah, that's they have tricks for doing that. Actually, I just realized that I don't know how they are, but they can compute, for example, this hopping thing. They have done that in numerics, and but it's I have to check how they do that. Yeah. But they claim they can do it. Yeah.
So we're good. Yeah. More. Okay. So
Great.
let's take it from another
Thank you.
time.
Oh. Hi, Charlie. How are you?
Good. It's actually